Hey, this is day 12 of running with Dappa. Today I have on my glasses. This is a new fit. My lock sock upon a new style. This is my black at Microsoft shirt. I represent for the ERG. Most of them are show up. We're in front of a plant today for extra aesthetic. And the shoes. Yeah man, see that basketball knockoff Nike here. And a gray shorts. Let me get. Remember me get it. But we're here guys. Another day, another dollar. We're doing the thing that we have to do to get fit for good, you know what I mean? Today is also indoors. It's just looking like an indoor thing, I know my friends. I know you guys like the views of the outside on thing, and it's kind of weird to just see somebody jogging on the inside, but remember, this isn't necessarily for content, but more so about accountability. So if you're watching with me, keep watching. One of my friends says she subscribe. Big up V. She subscribed because she said that she watch it while she washing her plates. So if you're washing your plates and you want to run and you want to burn calories through me, you definitely can do that. I'm sure you guys saw my promo video the other day. Big up to Kevs. She did a promo video for me. See, go watch it. Go watch it. I'm gonna put it on my YouTube later on as well. But subscribe, like, share, comment. Here. We're gonna do the same drill as we've been doing a couple times now. Playing a video when I'm silent, so you guys can take in some content. Tech videos because, of course, I'm in tech. But I understand if you're not watching past 5 minutes, you're not really expect to hear that. So I'll just go and chill for the first 5 and then I'll put on a video. Same need code video, or maybe couple of the ones from YouTube to hear what's up with the world of tech and all that. Anyways, I'm gonna speed up. Big up on yourself. We're there up on the gully side. I'm gonna plant your youth. Grade 12. Yeah, maybe they're fun there. Maybe we can put on the phone. Yeah man, there peeps. I go on easy back. Last 2 days, I'm gonna do this, I've been sweating out, so I needed a fan. Because the indoors is kind of hard. I think in the gyms they have AC. Here we don't have AC. So running it off, you know what I mean? Wanted to give a new look in the glasses, and we just get it prescribed and everything. First week of wearing it fully, or no, second week maybe. Anyways, y'all, we're running at onto the speed zone 3.0 2.8 and 3.2 miles per hour. Heart rate zone 2 119 beats per minute for now. So remember yesterday I was saying that it was hard, I did something, it was a little bit difficult to do. I think I caught it now. This pace, spaced repetition thing has been very helpful. You're learning technique of just, sometimes we bash the things we do at primary school, but it's really good. Where you do a math problem today, and then you do a next math problem the same day, the next day, but it's just retesting that you know what happened the week before. That then just a little twist, so your mind start thinking. I think those things are very important, even though it's structured. You know, sometimes structured learning get bashing, but I think we need to focus on like how to learn, when instead of just like just giving people curriculum and say, oh, do this, saying, oh no, this is actually a technique that is teaching you how to learn this, and the reason why we're giving you repetition like this is because this has been proven to help you remember better without trying to memorize, when you build your intuition for problems in this class of problems. So I wish that, I don't know, even like physics lessons back in the day, I wish they started off with like, hey, this is the, like during high school, this is like the context of where we are today. This is what's being done in research now. And people gonna be, you know, a little bit overwhelmed, but at least you give a little bit of historical background of the things that you are doing in high school is so quote unquote established, but at the time that they were being discovered and researched, they weren't established. So what are the stuff now that are being talked about that may or may not be established, and they give people a sense of intuition of saying, hey, I want to also get into that. I think instead of just having people just being molded to be doers and planners, as my archetypes from video 3, you also get a mind of creating, you know what I mean? Yeah, so we're here, we're doing the right thing. I don't know if you guys remember the archetypes that I talked about. The creator, the doer, the planner, the commentator, and well, I guess the creator will switch to creative. I switched it offline, sorry. So commentator, creative, planner, doer, consumer. Yeah man, so instead of just creating doers, we also can create some creatives through the process of structured learning as well. I think sometimes we have a dichotomy of creatives are unstructured and doers are structured. We can do multiple things at the same time. We can kill 46 birds with 2 stones. So how many stones was used to kill those 46 birds? If you actually think about it, I said 2 already. You never have to do a calculation. But just because you hear that in the structured learning, you think that, oh, some process need to be happening. Those are the things that make creatives thrive. Sometimes creative is just ostracized. Anyways, that's, as you know, from my 3rd video, I wanted to mold that part of my mind sometime. But anyways, we're out here, we're listening to some videos again. We did the whole recursion video and Fibonacci sequence, and we did the dynamic program equivalent, where instead of, so yeah, memorization that turns a Fibonacci sequence into something where you use a dictionary to hold the values in the meantime while you go down the stack, or yeah, go down the stack trying to figure out like the sub problems from top down, and it's more recursive, but using a cache to help you. Dynamic programming now is the mechanism of doing it from the bottom up and more iterative. So you know that the first value is the base case. You start from the base case and go up, as opposed to starting from the top case and go down. The dynamic programming part makes a lot more sense now. You define fib dp for I in range 0 to n. And you say if I equals 0 or I equals 1, return our memo at 1, which is the array. Memo at that position is equal to 1, Or else, if it is not that, it doesn't fit that condition of equal to 1 or 0, then you say memo at that position, which is the position I, is now equal memo at I minus 1 plus memo at I minus 2. And then you return memo. We're going to give a quick peek at the solution at the end of the video. But yeah, that's dynamic programming. We're going to tune into a video now on that. How to solve any interview problem, mastering dynamic programming, tech with Nicola. That's the video.
Summarize. In this, dynamic programming is a powerful design technique that combines the correctness of brute force and the efficiency of greedy algorithms. There are two common use cases for it. Finding an optimal solution, for example, when we want to find a minimum or a maximum answer to some question, or counting the total number of solutions that some problem may have. These are not the only types of problems that DP solves, but they're the most common. The method was invented by Richard Bellman in the 1950s. Dynamic programming is somewhat of a weird name, so don't look too much into it. Fun fact is that Bellman invented this name because he wanted to hide the fact that he was doing mathematical research. The reason he was hiding this is because the Secretary of Defense in Washington had a pathological fear and hatred for the word research. Using the term dynamic programming made it hard for anyone to express disapproval, as it was quite generic. Dynamic programming appears in many interview questions and is generally seen as a topic. However, if you understand the fundamentals and solve enough problems, you will get good at solving them, and who knows, maybe you'll even enjoy them. Dynamic programming is about identifying and solving all subproblems. While the general idea is simple, identifying what subproblem to solve can sometimes be hard. Good news is that the human brain is generally good at pattern recognition. So the more problems we solve, the better we become at identifying what subproblems to solve quickly. We will look at 4 problems in this video, starting with the basics. Future videos will cover more dynamic programming problems, so don't forget to subscribe to get notified. Let's start with a classic Fibonacci problem. We want to write a function fib of n that returns the nth Fibonacci number. The first and the second Fibonacci numbers are 1. To generate the next number,
some context on fib and like those kind of fractal methods and function. We're in a lot of African designs and like non-Western designs were fractal in how the design community is like swirling around the place, and you know it's like people say it's the function of nature. They were being looked down upon, and then you know we came up with this whole grid like structure for our roads. Everything is a grid. So there you go. In Canada, I used to live in Canada for what, 5 years. You have First Street down to 202nd Street. There's just one block was straight down. Over exaggeration, but you get it. Alright, I guess exaggeration because it's already over. But yeah, grid like. And then when it comes to like certain things from the continent or certain areas, you had more like a fractal design where things swirl around. There's apparently, I don't like the whole day's research without actually pointing to the research, so I'm not going to say that. But I've heard previous videos talking about the fact that people are more happy when in certain environments using those kind of designs versus like concrete structured, extra gritty. Gritty. Hey. Who know the gritty dance? Yeah man, I hate that. Yeah man, instead of being extra gritty, because yeah, more it's more reflective on nature. And yeah, anyways, big up.
Sum the previous two. For example, the sixth Fibonacci number is 8. We calculate it as the sum of the previous two numbers, which in this case are 3 and 5. Let's write a naive recursive solution to solve this problem. The base cases for the recursion are 1 and 2. Otherwise, we return the sum of the two previous Fibonacci numbers. This is a very simple solution, but it has a problem. Let's print the 7th Fibonacci number. We get 13. But what happens if we try to print the 50th Fibonacci number? It's very slow. Let's see why by visualizing how this function is executed. To calculate fib of 5, we need to compute fib of 4. And then to calculate fib of 4, we need to compute fib of 3. And to compute fib of 3, we need to compute fib of 2. Finally, we know that fib of 2 is the base case, so we return 1. We continue calculating fib of 3, which requires now fib of 1, that's also 1, and we finally can say that fib of 3 is 2. We go back to calculating fib of 4, now we need fib of 2 again. So this is 1, and the sum is 3, so fib of 4 is 3 now. Now we go back to calculating fib of 5, and we need the second part of the equation, which is fib of 3, and to calculate fib of 3, we go through the same process again. So we need fib of 2 and fib of 1. Now we can sum these and get 2, and finally we can calculate fib of 5, which gives us a result 5. As you can see, this was a very long process and a lot of iterations just to get to the result for fib of 5. Can you tell me what the time complexity of this function is? We can assume that the numbers fit in a word, which means additions are fast. Let's say the running time is t of n, which is t of n minus 1 plus t of n minus 2 plus O of 1. Constant is for additions and other simple operations that we run in this function. The time complexity is the same as the nth Fibonacci number, which is the golden ratio to the nth power, meaning it's very slow. Another way to look into this is to see that t of n is at least 2 times t of n minus 2, because the bigger the n is, the more work we need to do. This means that the time complexity doubles for each recursive call, and we are subtracting 2 until we get to the base case. We can subtract this half n times, so the complexity of this function is at least O of 2 to the power of n over 2. Notice that we are doing the same computations multiple times. For example, we have already computed fib of 3, but we are repeating the computation later. We should only do it once. There is a general approach to improve algorithms like this one, and this approach is called memoization, which means remember in Latin. Let's go back to our implementation. The idea is to remember the computation of each Fibonacci number and compute it at most once. We can do this by storing the computed value in the dictionary. Let's call it memo. Memo is initially empty. Next time we want to return the n, we first check if it's in the dictionary, and if so, we don't need to run the whole computation. The computation dictionary lookup. Notice that the memoized solution is almost identical. This means that you can convert to memoized approach for any recursive algorithm in general. Let's see how this algorithm runs with memoization. If we run fib of 50 now, we get a result very quickly. So can you tell me what is the running time complexity of the memoized solution? Well, notice that the recursion is rare in this case. The function will call the recursion only the first time for each value n. Next time, it will retrieve the value from the dictionary, which is fast. This means that the number of non-memoized calls is...
I want to run back something. I think I saw a formula that I want
and
to...
if so,
note.
Next time we want to return the this half n time.
Time complexity formula.
So the complexity of this function in general most once. We can do this by storing the computed value next time by the patient. If we run fib of 50 now, we get a result very quickly. So can you tell me what is the running time complexity of the memoized solution? Well, notice that the recursion is rare in this case. The function will call the recursion only the first time for each value n. Next time, it will retrieve the value from the dictionary, which is fast. This means that the number of non-memoized calls is n. Each non-memoized call, ignoring the recursion part, takes O1 to compute. This is why the total running time complexity is linear. And this is the fundamental idea of dynamic programming. Remember the solutions and try to reuse them to solve bigger problems. This is why the biggest challenge when designing a dynamic programming solution is to figure out what are the subproblems that can help you solve the actual problem. So, to summarize, in this implementation, we started from the final problem and recursively computed the subproblems when needed. Another way to look at dynamic programming problems is to start from the bottom up, which means compute the subproblems first. Most people prefer this approach because it doesn't have function calls, which is more efficient in practice. It also allows us to save memory in some cases. For example, to compute Fibonacci, we only need to remember the last two values, so we can delete one if we need it anymore to save space. Notice that the solution is the same as the memoized approach, except that we are storing the computed values in the dictionary and iterating over subproblems with a for loop instead of using recursion. When we compute the ith Fibonacci number, we are assuming that the previous two are already computed. This means that we need to put a bit of thought into the order in which we solve subproblems. It's important to solve dependencies of a subproblem first. Therefore, we have to solve the subproblems in the topological sort order if you imagine each subproblem being a node and the edges representing dependencies between subproblems. The dependency DAG for Fibonacci subproblems is very simple. Nth number depends on the n-1 and n-2 and so on. It's usually obvious in what order we need to solve subproblems, but the subproblem dependencies must not form a cycle because it would be impossible to store them in the topological order. Let's move on to the next problem. Given a set of coin values C1 to Ck and the target amount of money M, what's the minimum number of coins that can produce the given amount? For example, let's say that we want to give a customer 734 cents in change using euro coins. Possible euro coins are 1, 2, 5, 10, 20, 50, 100 and 200 cents. The optimal solution is to select 3 coins of 200, 1 coin of 100, 1 coin of 20, 1 coin of 10, and 2 coins of 2 cents. Do you notice anything interesting here? Well, we're always choosing the largest possible coin until we get to the target amount. This is called the greedy approach because we're choosing the greediest option every time, and it turns out this works for euro coins. However, it's not immediately obvious that this approach works and actually doesn't work in the general case. For example, imagine that the coins are worth 1, 4, and 5 cents and the target sum is 13. The greedy approach would produce 2 coins of 5 cents and 3 coins of 1 cent, which is 5 coins in total. However, the optimal solution is to use 2 coins worth 4 cents each and 1 coin worth 5 cents. Can we use dynamic programming to solve this problem? If so, what subproblems do we need to solve? It's usually a good idea to consider the final question you're trying to answer to also be the subproblem for dynamic programming. In this problem, the question is, what's the minimum number of coins that can produce the sum m? If this was our subproblem, what would be a recursive formulation to solve it? Let's say that the function minimum coins represents the minimum number of coins required for a sum m. Clearly, our base case would be minimum coins of 0 equals 0 because no coins are required to form an empty sum. Now let's try to solve a general subproblem, minimum coins of m, assuming that m is greater than 0. Remember when I said that dynamic programming is a bit like a brute force? If we were to implement a brute force solution, how would we do it? If we want to get to the sum 13, we can do that by choosing any of the coins. If we choose coin 5, then we have 1 coin and we're left with solving the same problem for sum 8. Similarly, if we choose coin 4, we have to solve the same problem for sum 9. And if we choose coin 1, then we have to solve the problem for sum 12. We will keep doing this until we get to the initial position, which is our base case 0. However, notice that we can't go below 0, so we will only choose coins that lead to possible states. For each node in the tree, we try all the possible coins and take the best solution. With this in mind, we can define the recursive solution as minimum coins of m is 0 if m is 0, or we take the best solution after choosing all possible coins c for m greater than 0. Let's try to implement this using the naive recursive approach first. Let's write a function minimum coins. The base case requires no coins, while in other cases we want the minimum across all subproblems, plus an extra coin to get to n. Negative subproblems don't exist, so we ignore those. We're using the min ignore none helper function to ignore none values because some subproblems may not have a solution. Let's run this function for sum 13 and coins 1, 4, and 5. We get the result 3 because we can form 13 as 4 plus 4 plus 5. What happens if we run it for the sum of, say, 150? Similar to the recursive Fibonacci, this is very slow. Luckily, we know about memoization, so we can use this trick to speed up our solution. Let's store the computation in the memo dictionary and return it if it's already computed. This solution is much faster and returns the value 30 immediately. The reason this function is efficient is because the answer for each subproblem is calculated recursively only once. After it was computed once, it can be efficiently retrieved the next time the function is called for the same parameter. The time complexity is O of m times k, where k is the number of coins and m is the target sum. This is because we iterate over each coin to find the best solution for each subproblem. Now let's provide a bottom-up solution using a loop to calculate the solution for all the sums up to, provided we iterate over each coin to find the best solution and efficiently retrieve the next time the function is called for the same parameter. The time complexity is O of m times k, where k is the number of coins and m is the target sum. This is because we iterate over each coin to find the best solution for each subproblem. Now let's provide a bottom-up solution using a loop to calculate the solution for all the sums up to n. First we store the solution for the base case, which is 0. Then iterate over each subproblem and each coin type. Ignore the negative subproblems and keep the best solution. Negative subproblems. We're using the min ignore none helper function to ignore none values because some subproblems may not have a solution. Let's sum 13 and coins 1, 4, and 5. We get the result 3 because we can form 13 as 4 plus. If we were to implement a brute force solution, how would we do it? If we want to get to the sum 13, we can do that by choosing any of the coins. If we choose coin 5, then we have one coin and we're left with solving the same problem for sum 8. Similarly, if we choose coin 4, we have to solve the same problem for sum 9. And if we choose coin 1, then we have to solve the problem for sum 12. We will keep doing this until we get to 4 and 5 cents, and the target sum is worth 5 cents. Can we use dynamic programming to solve this problem? If so, what subproblems do we need to solve? It's usually a good idea to consider the final question you're trying to answer to also be the subproblem for dynamic programming. In this problem, the question is, what's the minimum number of coins that can produce the sum m? If this was our subproblem, what would be a recursive formulation to solve it? Let's say that the function minimum coins represents the minimum number of coins required for a sum m. Clearly, our base case would be minimum coins of 0 equals 0 because no coins are required to form an empty sum. Now let's try to solve a general subproblem, minimum coins of m, assuming that m is greater than 0. Remember when I said that dynamic programming is a bit like a brute force? If we were to implement a brute force solution, how would we do it? If we want to get to the sum 13, we can do that by choosing any of the coins. If we choose coin 5, then we have one coin and we're left with solving the same problem for sum 8. Similarly, if we choose coin 4, we have to solve the same problem for sum 9. And if we choose coin 1, then we have to solve the problem for sum 12. We will keep doing this until we get to the initial position, which is our base case 0. However, Notice that we can't go below 0, so we will only choose coins that lead to possible states. For each node in the tree, we try all the possible coins and take the best solution. With this in mind, we can define the recursive solution as minimum coins of m is 0 if m is 0, or we take the best solution after choosing all possible coins c for m greater than 0. Let's try to implement this using the naive recursive approach first. Let's write a function minimum coins. The base case requires no coins, while in other cases we want the minimum across all subproblems plus an extra coin to get to n. Negative subproblems don't exist, so we ignore those. We're using the min ignore none helper function to ignore none values because some subproblems may not have a solution. Let's run this function for sum 13 and coins 1, 4 and 5. We get the result 3 because we can form 13 as 4 plus 4 plus 5. What happens if we run it for the sum of, say, 150? Similar to the recursive Fibonacci, this is very slow. Luckily, we know about memoization, so we can use this trick to speed up our solution. Let's store the computation in the memo dictionary and return it if it's already computed. This solution is much faster and returns the value 30 immediately. The reason this function is efficient is because the answer for each subproblem is calculated recursively. After it was computed once, it can be efficient function is called for the same parameter. The time complexity is O of m times k, where k is the number of coins and m is the target sum. This is because we iterate over each coin to find the best solution for each subproblem. Now let's provide a bottom-up solution using a loop to calculate the solution for all the sums up to n. First we store the solution for the base case, which is 0. Then iterate over each subproblem and each coin type. Ignore the negative subproblems and keep the best solution. Notice that we are calling the function get on the dictionary, which returns none instead of the key is missing. Both memoization and the bottom-up approach are. The bottom-up approach has a lower constant factor and it's slightly shorter, which is why I personally prefer it. From now on, I will only use the bottom-up approach in the final solutions. Nevertheless, it is often easier to think about dynamic programming problems in terms of recursive functions, so the thinking process will remain the same. Now let's see a variant of this problem. Instead of finding the minimum number of coins to form a sum m, let's find in how many ways can we form the given sum m. For example, given coins 1, 4 and 5, in how many ways can we form a sum of 5? There are 4 ways in which we can do that. Using all ones, using 1 and 4 and vice versa, and a single coin 5. Let's try to construct a recursive solution. Choosing a coin 5 takes us to 0. 0 is the starting point, so it's a good candidate for the base case. The question is, what is the answer for the base case? In how many ways can we construct 0? Well, our only option is to choose no coins, so that's one way in which we can form the 0. This path represents the choice of a single coin with value 5. Another option is to choose coin 4, which takes us to the subproblem 1. In how many ways can we construct 1? To find the answer, we solve the subproblem for 1. We repeat this process for every coin. In the final solution, we want to know in how many ways we were able to reach 0. We can take the sum of solutions across all subproblems to get a final answer. Let's go and implement the bottom-up solution. Note that this is going to be very similar to the previous problem. The only differences are the base case and taking the sum instead of the minimum. Let's run this solution on the example we saw earlier. Before finishing this video, let's look at one more counting problem. Imagine an n by m grid earlier. Before finishing this video, let's look at one more counting problem. Imagine an n by m grid. A rabbit is in the top left corner and wants to go to the bottom right corner. It can only go down or right. In how many ways can it reach the bottom right corner? For example, for a 2 by 3 grid, there are 3 ways in which the rabbit can get to the bottom right corner. Right down, right, and down right. Again, let's start in the exact same way as before by defining a subproblem. Our goal is to find in how many ways the rabbit can get to the bottom right corner, given the grid n by m. So let's use that for the subproblem. It's helpful to visualize the problem, so let's look at a bigger 6 by 9 grid. If the rabbit moves down, then we are reducing the problem to a 5 by 9 grid, because it can't go back. Similarly, if the rabbit moves right, then we are further reducing the problem to a 5 by 8 grid. Since the rabbit can only move down or right, we are always reducing the problem to a smaller grid. Notice that when the rabbit gets to the last row or column, it can only keep moving in one direction until it reaches the bottom right corner. Once the rabbit gets to the bottom right corner, it has no more moves left. It's often useful to think about corner cases like this one when trying to construct a base case. In this case, we can say that the rabbit has only one way to get to the bottom right corner for a grid of size 1 by 1, which is by not moving at all. Okay, so let's go back and try to construct a recursive solution. If we want to solve the problem for a 4 by 6 grid, in how many ways can we do that? Since the rabbit can move down or to the right, we need to take into account both options. If the rabbit moves down, then the number of solutions is the same as for the grid 3 by 6, and if it moves to the right, then the number of solutions is the same as for the grid 4 by 5. Since it can go in either direction, we can take the sum of both subproblems. Also, notice that our formula doesn't quite work when one of the coordinates is 1 because it requires the solution for the grid of size 0, which we haven't defined. One way we can solve this is by expanding on our base case. For example, we can say that a grid with at least one dimension of 1 is the base case because we already know that there is only one way to get to the bottom right corner once the rabbit gets to the last row or column. Let's try to convert this into code. We want to populate the memma dictionary such that memma of n, m gives us the solution. Let's initialize the base cases first by iterating over all grids with at least one dimension of 1. We can do this with 2 for loops. After initializing the base cases, let's populate the memma dictionary for all sizes using our recursive formula. We start from the size 2 by 2 because the grids including size of 1 are base cases. Finally, we return the solution for n by n. How many paths do you think exist for an 18 by 6 grid? What about 75 by 19? Okay, so we have solved a couple of basic dynamic programming problems at this point. In the future videos, we will tackle more complex ones. I'd like to finish this video with a couple of important points that you should take out from this video. When you're trying to solve dynamic programming problems, start by defining the subproblem. For simpler problems, subproblems usually have the same form as the actual problem. After defining a subproblem, try to figure out what is the base case. Finally, try to come up with a recursive formula that solves a generic case. And remember, visualization is your friend here. Don't forget to subscribe to get notified about the future dynamic programming videos. Also, if you've enjoyed this video, please hit the like button because it will tell me that it's worth making content like this.
Okay guys, go subscribe with Tech with Nicola and like that video. But before you do that, I want you to like this Dappa vid to get running with Dappa. Today we are at day 12 and I want you to like it and destroy that subscribe button. Mash it up, mash it, and then have fun in the chat. Chatter. Tell me what you learn. I know what I learned. And I'm going to try them out on my whiteboard, aka my mirror, and do my thing. going to run over to neat code for the last 20 minutes of this beautiful run at 3.8 kilometers per hour at a distance of 2.0 kilometers done, 160 calories burned. The zone of zone 3, 151 beats per minute, 5,700 steps. Yep, 40 minutes down, 20 to go. And we still have 1/3 of the way to go. You have to keep pushing, get through that halfway mark. But if it's hard to start, just say you're going to run for 5 minutes. 5 minutes. And if you have a quick duty to do in the household, let's say you're going to do it in 1 minute and start rushing. KKBT, my love. Yeah, man. Woo. We here. Let's stay with you a little bit. Insertion sort as well. We're talking about how to do a iterative insertion sort algorithm. That was fun. Now we're gonna be doing some merge sort. This is the question that I got at my interview. Merge 2 sorted arrays and then merge 3 sorted arrays or something like that. And I went through. Let's see how much I remember from 4 years ago.
Efficient algorithm. The main idea is to take the input array and then split it into 2 approximately equal halves. And then for those halves, split them into approximately equal halves, and then continue to split each subarray until we can't split them anymore, which would mean we have individual elements left for us to then sort. The idea is to break up the original problem of sorting the entire array into subproblems. So in order for us to sort the entire array, first we can sort the first 3 values, 3, 2, 4. So we can sort the first half of the values. In this case, we have an odd number of values, so we can't split it exactly into half, but more or less it's approximately half. And then the second half of values, we want to sort these as well. But then for these subarrays, we also have subproblems. We can split this array into half, the first half and the second half, and sort those portions of the array before we sort this original array. And the same thing for here. You can see that since we have a natural way of splitting this into subproblems, until of course we reach the base case where we just have subarrays of a single element, like down here as well, this problem naturally lends itself to recursion. I promised you that recursion was going to come up a lot more, and this is one of those cases. And this is clearly 2-branch recursion because we're splitting this into 2 halves. And I'll talk later why exactly we're splitting it into halves. But to give you a hint, as you know, the number 2 is pretty important. And as we take the array and divide it by 2 each time, that lends itself to be an efficient algorithm. We'll talk about that more a little later. But this array as well is being split into 2 halves, 2 branches. This array, same thing. But these are the base cases. Now we talked about how we're going to divide this into subproblems. By the way, the technique we're using right now is sometimes called divide and conquer, because we're taking the original problem and dividing it into subproblems and then solving those subproblems before we solve the original problem. But I haven't talked about how we're even going to solve these subproblems and what we're going to do once we have that done. Well, let's start on the left side. We're going to first take this array, get the left half of it. We're going to take that and get the left half of that. And then we're going to take this and then split it into 2 individual elements, 3 and 2. Now this is technically a sorted array, and this is technically a sorted array. When you have two sorted arrays, we can merge these two arrays back into the original array such that they are in sorted order. That's why this is called merge sort, because we break it up into two subproblems and then merge them back together. So for getting the original values that were in the array, we create a copy of the value that was here, and we create a copy of the value that was here. And in this case, it's pretty simple because we just have two elements. So we're going to compare these two. Which one is smaller? 2 is smaller. So the 2 is going to go over here, and the 3 is going to go over here. Now from the perspective of this array, we've solved the left subproblem. We have this portion sorted. Now we need this portion sorted. Well, it's just a single element, so this is the base case. So now we don't care about the original values that were over here. We have two sorted arrays and we want to merge them together into the original array. In general, the algorithm is going to be 2 pointers for us to do that. We're going to start at the beginning of this array, and we're going to start at the beginning of this array, and we're going to compare the values, because we know at the beginning of each array is going to be the smallest value, because this is sorted and this is sorted. So we're going to compare the two values. Which one is smaller? 2 is smaller than 4, so 2 is going to go over here. The pointer that was over here is now going to be shifted to be over here. And now we're going to continue the algorithm. We're going to compare the value here to the value here. Which one is smaller? 3 is smaller. So the next value that we insert is going to be 3 in the next position of this array. And at this point, our pointer that was in the first array is now going to be out of bounds. So at this point, we have no choice but to place the value from the second array in the next spot, which is also the last spot. So we put the 4 over here. So now we finally arrive back at the original problem we were trying to solve. We sorted the left half of the array. Now it's time for us to sort the right half. So then we have this portion. We break it up into individual elements. We don't care about what's originally here. We compare these two values. Which one is smaller? 1 is smaller than 6, so we put a 1 here. That is what the original value actually was, and we put the 6 here. So in this case, the original was already in sorted order, but we still had to do this work anyway. But now that we took the original array, have it sorted into a left half and a right half, we can merge these two portions together to make the original array sorted. So forgetting about the original values that were over here, we again use our 2-pointer technique. We have a pointer at the beginning of the left array and a pointer at the beginning of the right array. We compare the values. 1 is smaller than 2, so we're going to take the 1, put it at the beginning, and then we're going to shift the pointer that was here to be over here. By the way, we are going to have a third pointer in the output array. It's going to tell us where we should insert the next element. Originally it's over here. Now that pointer is going to be over here, and then next it's going to be over here, and then here, and then here, and keep going until we run out of elements to insert. But right now we're going to be comparing the 2 and the 6. Which one is smaller? The 2 is smaller, so we're going to insert the 2 over here. We're going to take the pointer that was at the 2 and then shift it to the right to be over here. And we're going to repeat. Which one is smaller, 3 or 6? 3 is smaller, so let's put the 3 over here and then shift the pointer to be at the next element. Let's compare these two again. 4 is smaller, so we put the 4 over here and then shift our pointer to be over here now. It's out of bounds, so we have nothing left to compare this 6 to. So at this point, whether we have one element over here or maybe we would have a couple more elements over here, regardless, since we ran out of all elements of one of the arrays, at this point we would just fill in the remaining spots from the other array that's non-empty. So in this case, we only have a 6, so we put the 6 here. But if we had more elements like a 7 and an 8, we would just start filling them over here. So taking a quick look at the code, like I said, this is going to be a recursive algorithm, clearly, where we're breaking it up into 2 steps. So this is going to be 2 branches of recursion. Now into this merge sort function, I'm passing in the starting index and the ending index as well as the array that we're actually going to be sorting. That's because as we break this up into subarrays, we don't necessarily have to create a variable for each subarray. We can just kind of keep track of this half based on the starting index and the ending index, rather than actually creating a brand new subarray like that. But how do we know if we've reached the base case? Well, if the length of the subarray is less than or equal to 1, well, how do we get the length itself? We can take the ending index minus the starting index plus 1. So basically, this element by itself is at index 0. So what we do is take the ending index, which is 0, minus the starting index, which is 0, plus 1 gives us 1. So this is of length 1. So that's how we know it's a base case. That means it's already sorted, so we can just return the array itself. But if we got to a case like this one where the starting index is 0 and the ending index is 1, then we're going to get the ending index minus the starting plus 1, which is going to give us a length of 2. That's correct. This is length 2. But that means our length is not less than or equal to 1. So what we have to do is calculate the middle index between these two. So we take the starting plus the ending and divide it by 2. So 0 plus 1 divided by 2. So most programming languages will round down. That's what we want to do, round this down. So a 1 divided by 2 is going to evaluate to be 0. So we're going to say the middle index is 0. This is the middle index. So what we're going to do now is break this up into 2 halves. We're going to call merge sort from starting to middle. So in that case, this means call merge sort on the array starting at index 0 and ending at the middle index, which is 0 as well. So we're going to call, basically that evaluates to this. We're going to call merge sort on just the first element, and we're also going to call merge sort on the second half of the array. So from index m plus 1, which is 1, and the ending index, which is also 1. So that's pretty much correct. We're going to call merge sort on this portion of the array. And these, of course, are the base case. So after we call merge sort, we're going to expect those 2 halves to be sorted. So then what we're going to do is merge those halves together. Now, I haven't shown you the implementation of this. It's not super complicated. It's just a decent amount of code. It's basically the 2-pointer technique we were talking about a moment ago. But what we're saying with this function call is merge the left half of the array, which starts at index s and ends at index m, and merge that with the right half of the array, which starts at m plus 1 and ends at index e. So it will basically merge these two together into the original 2-element array. Now I will say when we do merge the left and right half together, we do need to create extra memory. So for the left and right half array, we're going to create temporary arrays. So we are going to create copies of the left and right half arrays, but we're only doing that for the merge step. So only when we start to actually merge them together into the original are we going to create those copies so that we don't lose what the original values were. So in general, we start out with a big problem, we split it into 2 sub-problems, solve the sub-problems, and then merge the result of the sub-problems together. Now in terms of time complexity, this is a relatively efficient sorting algorithm because we're splitting it into halves. We're doing that on purpose because it does make things more efficient. So the first question is, starting with an array of length n, how many times can we split it by half? In other words, how many levels are there to this recursion? Because it's going to be the same number of times where we can take n and divide it by 2. Because here we have, let's assume actually we just had 4 elements to keep the math simple. We would have 4 elements. We would split it into 2 elements on each side, and then we would split it into one element on each side, and these two wouldn't exist. I'm doing this just for simplicity, but we start with n equals 4, we divide it by 2, so n equals 2, and then we divide it by 2 until n equals 1. We know when n equals 1, that's our base case. So what's the math formula for how many times we can take this number and divide it by 2 until it's equal to 1? Well, if we were starting at 1 and then multiplying it by 2 every single time, that would be something like 2 to the power of n. But we're doing the reverse of that. We're dividing it by n. So what we're asking is we have a number n and we want to divide it by 2 and then divide it by 2 and then divide it by 2, which is the same as saying 2 times 2 times 2, etc., right? Which is the same as saying 2 to the power of some variable like x, right? This is the number of times we're going to divide this by 2, and we want to keep dividing it by 2 until it's equal to 1. Well, by doing a little bit of algebra on this, we can rearrange this to be the same as n equals 2 to the power of x. We care about x. That's how many levels are going to be in this merge sort algorithm. So how do we solve for x? Well, in case you forgot a little bit of math, I'll tell you, we can take the log of both sides of this equation. That will give us, and by the way, I'm doing log base 2. Log base 2 of n is equal to log base 2 of 2 to the power of x. And if you forgot your log operations, this can be simplified to take this x away and put that x over here. Now, log base 2 of 2 is the same as saying 2 to the power of what is going to be equal to 2. Well, 2 to the power of 1 is equal to 2. So this whole thing, log base 2 of 2, simplifies to be 1 is what I'm getting at. So what I'm saying is we already solved for x. X is equal to log base 2 of n. So what I'm saying is, if we have a number n equals 4, or any number, how many times can we divide it by 2 until it's equal to 1? Well, our answer is log base 2 of n. Log base 2 of that value is how many times we can divide it by 2 until it's equal to 1. And this turns out to be a reoccurring theme throughout algorithms and data structures. It's something we're going to see a lot more throughout the course. And this is kind of the math background of why most people don't touch on this and most people never learn it and never understand it. But I wanted to explain it to you because I touched on a reoccurring theme throughout algorithms and data structures. It's something we're going to see a lot more throughout the course. And this is kind of the math background of why most people don't touch on this and most people never learn it and never understand it. But I wanted to explain it to you because I think thinking about it this way and understanding your thought process is very important throughout algorithms and data structures. It's really what separates beginners from people who can solve problems on their own. So we did all that work just to figure out that the height of this is going to be log base 2 of n. I'm going to usually omit the 2. Usually it's implied that logs are base 2 most of the time, but that's not the entire time complexity. That's the number of steps that we're going to have. But what's the time complexity of each step of this algorithm? Well, it's big O of n. Let me tell you why. Basically, it has to do with this merge step. So suppose we're at this step of the recursion. We have our subproblems here and here, and now we want to merge them together in this array. What are we going to have to do? We're going to have to iterate through every element in each of the subarrays, which is going to result in an element being put in each spot in the original array. So basically, for this step, we're going to have to iterate through every position of the input array. So that's clearly an O of n time operation. But my argument is...
Alright people, 1 minute left. Thank you for watching. If you're watching up until the end, you know, stay thriving, stay winning. Keeping yourself accountable to a bigger goal. Start small. Time box yourself. And push through. And you know what to do. Give me a like, subscribe, share this video to share some either coding questions or running motivation, or if somebody just want to chill with, we outside. No, we inside. Big up yourself. Take care. 2 seconds. I'm out.